Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is minimum height trees. So the problem statement goes like this. You will be given a tree which is by the way an undirected graph in which any two vertices are connected by exactly one path. In another words, you can say that any connected graph without simple cycles is a tree. So you will be given a tree, okay, and there are n nodes in that tree. Given a tree of n nodes, and those nodes are labeled from 0 to n minus 1, okay, and which is the whole tree is indicated by an array of n minus 1 edges, okay, where if each entry in this edges array represents that, let's say this is the entry, that there is an undirected edge between two nodes A and B, okay, these two nodes. So you can choose any node of the tree as root, okay. So these are the different nodes of tree chosen as nodes, chosen as roots, okay. So when you select a node as a root, the resultant tree has some height, okay, from root to leaf nodes, okay. Among all the possible rooted trees, those with the minimum height are called minimum height trees, okay, MHTs. uh, okay, and you have to return a list of all the MHT root labels that can be there, okay. So these are the roots when these are the nodes when taken as roots will result into the smallest height trees, okay. So you have to return all those nodes which if taken as root will result into minimum height tree. So you can return the answer in any order, whatever order you prefer. The height of a rooted tree is the number of nodes on the longest downwards path from the root to the leaf, okay. So it means that if you are starting from the root, then till the very end of the end of that binary tree, or you can say leaf, how much is the length, that is the height of that particular tree, okay. So here you can see that when one is taken as root, it only it results into the smallest height tree. So one was the only node if taken as root which is resulting into minimum height tree. So that's why we returned one only as our answer, okay. So it is the only node uh, that if taken as root will result into minimum height tree. So let's have a quick look before thinking of an approach or getting intuition how to solve this particular problem. uh, According to the constraints, the number of nodes in the trees is of order 2 into 10 raised to power 4, and edges, total number of edges will be equal to number of nodes minus 1, okay. And each node number will be ranging from 0 to n minus 1, okay. And it is mentioned that there are no self loops. This is condition of self loop. It means that our node is not connected to itself, and all the pairs in the edges array that will be given to you are distinct, and it is guaranteed that the input that is given to you is of a tree. It means that there will be no repeated edges, and there will be no repeated edges. uh, by a tree it means that there will be no cycle, simple cycle, okay. So let's think of an approach keeping these constraints in mind. how to solve this particular problem. Basically, if you consider the whole tree as a shell like structure, just like onion having some rings, so you are interested in the, let's say, all the there are some nodes on each of these rings. Okay, so, or you can consider it like a atom also, and its orbits. Okay, so let's say there are some nodes, and these nodes are connected somehow. Okay, it means that there are some connections. Okay, so there can be some connections, and yeah, so just to give you an idea, now I am removing those connections. If we remove those connections, we will be seeing that, or let's say, let's restore those connections for once. Okay, so we will see well how many number of nodes node is connected to at present. Okay, so those nodes which are in this outermost ring, this ring, are connected to only one nodes. Okay, outside this ring there are no connections, but inside ring they are at least connected with you can say one node. Okay, so because they are connected with this inner ring, just one below the outer ring. Okay, so this is our outer ring, this one, and this is, okay, let's assume that each of these nodes are connected to somehow the inner ring. Okay, for now we are not concerned with how these connections are being made and to which node they are actually being connected to. So we assume that, okay, somehow these connections will be there. Okay, so they are connected to only there is only single collection for these nodes, not even double or edges coming to these nodes. Okay, so these are undirected edges, of course. And if I remove this particular ring, how will the new structure look like? So let's remove this one. Okay, so now the outer ring is being removed and our new outer ring is revealed, which is this one. Okay, so now you will see that these will be also having only single degree connections. I mean, there will be only one edge that is connecting them, okay, towards the inside rings. So let's remove this ring also. So I'm removing the inner ring, which have now become the outer ring. So there is only one ring left. When there is only one ring left, then nodes on that ring will be our answer. Okay, because these are the nodes. When they are taken as root, they will be forming the trees with minimum height. Why is it the case? Because if somehow there are some connections and these are the very center of those connections. Okay, so there are some connections going on outside, and let's say there are n number of connections. Okay, so this node which is at the very center is in the innermost, is representing the innermost ring. The nodes on is innermost ring. So these are nothing but rings. Okay, so like you are able to see that this one is connected to two nodes, one on the outer ring and one on the inner ring, and this one is only connected to only one node, which is this node. Okay, so we will first remove the nodes which are at present connected to only one node, which is the outer ring, just like I was removing the rings one by one. And when these connections are removed, this will be the outer ring. I mean, this node will now only be connected if this outer ring is gone, to only one node, which is the innermost one. Okay, so as when you are at the very innermost ring, then you will stop then and there, or you can say that we will take all the nodes that are in the innermost ring as our answer. Okay, so I hope you are able to relate with this analogy. And so this is nothing but a level order kind of traversal. Those of you who are not familiar with level order traversal of a binary tree, I will provide uh, a link of an article explaining this level order traversal, and then you can explore that link and then you can proceed further with this. This is just like a simple breadth first search. Okay, BFS. What you will be doing is, uh, let's consider one of these graphs. Okay, so let's take this one. We will be building a graph basically from the edges that we are given. Okay, so let's take the very first input. Let me zoom in a little bit. Okay, yeah, now it's fine. So let's make the connections. So one is connected to 0, then one is also connected to 2, one is also connected to 3. Okay, so this is the situation. This is the graph basically, or you can say tree. So let's form those rings that we were talking about. So rings will be formed in this fashion, and this one will be the on the innermost ring. Okay, so this is we drawing rings just by our observation or just by looking at the graph. How to do this programmatically is the further question that may come into your mind. So what we will do is we will be having an array which is connection degree, the number of connections or the number of edges that are connected to a particular node. So these one on the outer ring were having number of connections, connection degree of 1. So these were having only one connection degree. Okay, and when as when okay, sorry for the delay, there was some technical issue. So this particular connection node is having connection degree of 3, so it is connected to 3 nodes, or 3 edges are coming towards it, you can say, even though these are not directed edges. So this is the outermost ring, So we will be picking those nodes which are having connection degree of 1 right now. Okay, and we will add them in a queue. So these nodes are 3, 2 and 0. We will pick them one by one from the beginning of the queue. We will add them from the end, and we will take these node outs from the queue from the front. Okay, so one by one. So 3, we will explore all the neighbors of 3, the nodes to which 3 is connected to. So 3 was connected to only 1, so 1 was its only neighbor. So we will now decrement the number of connections. Okay, we are breaking this connection. This connection is now gone. And what will be the new connection degree of this one? It will be 2. Okay, and since 3 is not connected to any other nodes, if it was connected, then we would also have removed those connections, and connection degree of those nodes which were connected to 3 would have been affected. But there is only a single node here which was 1, so it is the only node whose connection degree is getting reduced. So similar thing we will keep doing for every node. Now 3 is gone, then 2 is also connected to only one node, so this connection is gone. Okay, and similarly it will happen for 0. As when the connection number of connections that a node is having is reduced to only 1 or 0, then you will be adding it to the queue. Okay, so this is the whole logic, and it will help you to reach in the innermost level. Okay, so this is the approach, and this is how we will be solving this whole problem. And let's have a quick look at the implementation of this BFS approach. Okay, let me quickly copy the code here. So this is the code. I think it is better for me to explain it here only, because otherwise it's quite a lengthy code. Or maybe we can break it down into some pieces. Let's try. Okay, I will be explaining right from here, or maybe it's better here only. Okay, let's take this to this level only. So what we will be doing here is, first of all, we will be making the graph. This is we making the graph. Okay, and also along with that we are increasing the connection degrees of each of the nodes, two nodes involved in this current edge. So when we are visiting a current edge from this edges array, then we are here increasing the connection degree of each of these nodes. Okay, and this is we forming the graph. Since it is a undirected graph, so we are just using this whole structure. This is your current node, and these are the neighbors of the current node. Okay, so for the node at the first index of this edge, okay, the second node will be a neighbor, and vice versa. Okay, that's why we are adding these nodes into as neighbors of each other. Okay, and then we are doing a BFS or level order traversal here, just like we remove the or peel the layers of an onion to reach the center. Similar kind of approach we are taking for taking to solve this particular problem. Okay, first of all, we are taking the nodes which are at the very outer ring or which are having only one connection as of now. So we will be pushing those nodes to the queue, and then we will be exploring their neighbors. Okay, and along with that we will be removing the connection of these nodes with their neighbors. Okay, so there is another variable which is nodes left. This is basically we are checking whether if we remove this layer of nodes, then how many nodes will be left. Okay, so as when you will be removing with the very last layer. Okay, if this layer is also, let's say these layers are removed and only this one is left. So if you remove this layer also, how many nodes will be left? Okay, let's say there were n nodes and you all already removed n minus 2 nodes. Okay, now only 2 nodes are left on the last layer. If you remove these nodes also, then the number of nodes that are left will be 0. So we will know that this is the last layer, and we will be taking those nodes which are on the last layer and we will be adding that to our result. Okay, so this is the thing that we are doing here. First of all, we are checking what is the size of the current level. Okay, how many number of nodes we will be removing if we remove this ring or this level. Okay, so nodes removed will be equal to that size, and then we will be let's say removing those number of nodes. So we will be decreasing the nodes left. Initially the number of nodes that are left will be equal to n, which will be the initial number of nodes. So this removal will keep happening, and this is just a simple BFS level order queue, level order traversal or BFS. And as when the number of nodes left are 0, it means that you are at the very last level. So you will be wanting to collect all the nodes that were present at that last level, and those nodes will be the nodes that we will be returning as your answer. So that's why you are adding them to the results array that you will be returning. And this is we removing the connections of the current node with its neighbors. Okay, and as when there is only single connection left, then you can say that okay, this particular node will be now forming uh, the next uh, outer ring. Okay, you can say. So if we removed the very first ring only, then let's say the next outer ring will be this ring. Okay, so this will reveal the next outer ring, this whole step. Okay, and yeah, and you will push the nodes that will form the next outer ring into the queue, and this thing will keep continuing like this only, and at last you will be returning your result. Okay, that is how you will be solving this particular problem. And if you ask what will be the time and space complexities, as you must have guessed that time complexity wise it's order of n only, since each node is being visited only once. Okay, and as far as space complexity is being concerned, so it will be the maximum number of nodes on a particular level. Okay, so that will be the size of the queue that will be required. Or if you consider this one also, uh, I mean it will be larger than that, lesser than that size, so it will be the space complexity wise, it you can say that it will be the maximum number of nodes at a particular level. Okay, level, or you can say ring. Okay, So these are the complexities. If you are still having any doubts or any queries in general, then you may ask them in the comment section. I hope this whole problem solving session and this solution walkthrough added some value to your DSA journey of owning your DSA skills. I will see you in the next video. Until then, keep practicing and keep solving problems. Thank you for watching.